Okay. So anyway, do you have any list of questions with you for those who are starting reading the paper? If not, next time I will advise you to bring, because after reading a paper, definitely you will have some questions. Maybe they are technical questions, or maybe they are like on the background. Like I don't know what is a functional unit. I don't know what is how prefetcher works. I don't know how this or that thing works. So if you have questions on that, so prepare a list and bring it to the Tuesday class, so that when I am like, yes, I will have my own material to like explain, but I would like to take your questions as well. Okay. Okay, so the paper we are going to cover in this week is a survey of microarchitectural side and covert channels, attacks and defenses. The paper was published in 2018. Why it is not mirroring? Last time it was. Strange. Okay. Okay. So the paper was published in 2018 in Journal of Hardware System Security by Yakub Zephyr. I haven't shown his name, the name of the author here. Okay, what is the motivation? Uh, Okay, remember it is not a research paper, it is a survey paper. So there is difference between the two kind of paper. Why in research paper we are basically trying to address a new problem, but in the survey paper we want to summarize in a systematic way the existing body of work. Okay, so here they want to like the motivation basically is like, let's say I'm a new person in the area and I cannot read thousands of papers related to hardware security and different domains within the hardware security. So, but as a new beginner, I want to have a quick overview of the domain of the area. So that is the purpose of this paper. So it will give you not the quick overview of the hardware security, but only a very particular stream, a very particular subset, which is about side channels, microarchitecture side channels, so that after reading this paper, if you are a researcher or a software developer, you know that the software you are going to run on a particular hardware platform, how it will behave on that platform and how it can be susceptible to the security attacks. So if you know that how it can become a victim of security attack, then maybe you can think about how to protect your software. Okay. So introduction. So let me first, I will explain these terms or terminologies later, like what is side channel or covert channel, or what is timing based, what is about timing when we say timing based side and covert channel. But let's first focus about why it is important to talk about timing based side and covert channels attacks, why we should think about them. because these kind of attacks, they can cause the leak of sensitive or private information of a person or a process or a program, which is run on a computer. And the strength of these kind of attack is that they do not need the physical proximity. By physical proximity mean that if I have a setup, and let's say I'm an attacker and I have a setup to launch an attack, that setup is not required, whatever setup it is not required to be physically located close to the platform where the victim's application is running. So it is possible, which basically means that, again, let me like break it down more further. Let's say I am an attacker process. Now I'm like, instead of saying attacker in abstract way, I'm talking about an attacker process which wants to launch an attack on a victim process, right? So if I use these kind of side channels to launch my attack, I don't need my process to run on the same computer as the victim process. So this is what is meant by physical proximity. And physical proximity is basically mean that the computer on which my process is running does not need to be closer to your machine. And another thing about, so they don't need the physical proximity if you are using these covert and side channel attacks to launch your side channels to launch your attacks. So like they are like the mean of launching your attack. And the second thing about their strength is that they even, so first was physical proximity, and the second was the co-location. So co-location is like the two processes are running on the same machine. Okay, so this, in most of the time they need co-location, but there are some examples of attacks which use the side channels or covert channels, and they even don't need the co-location. So which basically mean, an example is, let's say you are running a process or any application on your laptop, but you are connected with the internet, and the attacker application is maybe running, let's say, in another country of the world, on the other side of the world, but the attacker is also connected with the internet. So there is co-location, there is no co-location involved. The two processes are not running on the same machine, but still this kind of attack can happen if there is some kind of communication between the two processes. Okay, any kind of communication or interaction between two processes. Okay, so what is before talking about what is a covert channel or side channel, let's just first clarify what a communication channel is. So it is simple. In communication channel, you have two entities. One is the sender, one is the receiver, and between them there is a communication link over which they transfer the information, right? So this is like, not even if you don't talk about in context of the security or hardware security. So this is like a general concept, right? But when we talk about covert channel, so it is a channel that was not intended or designed for information transfer. So when the designers of the platform or the architecture, when they were designing the components of their architecture, they didn't want those components to transfer the information between them, like from component A to component B, or the software running on component A to the software component running on the component B. So what happened is that an attacker can later on discover a logical channel, or an attacker can abuse an existing channel to transfer the information. And here what happens is that you have a sender, which is like attacker, and it intentionally sends the information to the receiver. Okay. And again, remember, these channels are not logical, they're not physical channels, these are logical channels which you can build if you have insights on how the microarchitecture works. Okay. So, and the side channel is again similar as covert channel, but the difference here is that the transfer of the information from the sender to the receiver is not intentional. And here, unlike covert channel case, here the inside channel, the sender is the victim process on which you want to launch that attack. So what happened is that unintentionally, as a result of the implementation, how the hardware is implemented or how the hardware is used, as a result of that, what happens is that sender unintentionally leaks some information, and then the receiver, which is an attacker, can pick that information. Okay. So that's why it is called side channel. Okay. Channel capacity. Channel capacity is we define it as like how much information can be transferred between sender and receiver using that covert channel or the side channel in a given amount of time. So higher the amount of information or the data that can be transferred, higher is the leak of information, rate of leak, information leakage. And if, yeah.
Is it possible for an attacker to create a channel, or is it just a flaw in the design of in the whole architecture?
A sign of flaw in the whole architecture?
Yeah, a flaw on the design.
Yeah. So actually what happens is like, it is not correct to say that an attacker can build a channel. Because what happens is that whatever resources attacker uses to realize the channel, they are already there, but their original intention or the purpose of those components or resources is different than transferring the information. And that information transfer is not also in an explicit way. It is not like, okay, send 1 byte of data. It's not like that. You first discover some patterns in the execution of the victim or the attacker, basically victim, and then based on those discovered pattern, you build some information and then you transfer that information. So you are not actually directly getting the access to information of the victim. You first look on some patterns like what kind of instruction it is executing, what kind of memory, what kind of accesses is it making, what kind of predictions or mispredictions are happening when your victim is executed. So you look on those patterns, and based on that, you construct the information and then you transfer. When I say you, it's me. Okay. So you cannot say that attacker can build, let's say like this. Attacker can build the logical channel, not physical components. They are already there, but attacker just misuse them or abuse them. Okay. Any other questions? Yeah.
This is just from my understanding, but physical proximity is component A and component B are next to each other, say on the board, but co-location is just somewhere on the device. Is what I'm understanding.
What do you mean by device? How you differentiate the device and components on the board?
Like the same machine. Co-location is they have to be on the same machine.
Yes, that's correct.
And the physical proximity is just if the components are physically
next to each other. So let me give you an example. So example will make things more clear. So about physical proximity, it is like, let's say you are running an application on your processor, and I have a device which can perform the heat scanning, like how much when you're executing your application, how much heat is released by your laptop over the period of time when the application is running. So let's say if you run it for 100 hours, let's say in first 10 hours, the heat which is consumed is low. And then in next 5 hours, it is high, and next 2, it is relatively more low, and then so on. So there is like pattern. Okay. So based on that, so now this is my machine, which on the device, which is performing the heat scanning, is a different independent device, and it needs to be physically close to your laptop. Otherwise, I cannot do. Or like, let's say I'm using some radio device. Okay. So these are like examples where you are launching the attack, but the two devices need to be physically close to each other. In contrast to it, the co-location is where your two processes, the attacker process and the victim process, are running on the same machine. Okay. Thank you. Okay, so any other question or comment? Yeah.
Channels. So those are, well, no, I guess now I'm kind of getting all confused.
Okay.
So the channels, those are hardware and software, but there's a physical layer of those that are being built in that we can't access, but some are, but they're all within one CPU.
Let me give you an example. Again, as a side example will make the things clear, because you are right, there is a component, hardware component, there is a software component, but logically the channel covers the everything. Okay. So yeah. So let's say you are familiar with caches, right? Okay. So let's say you have a processor And on that processor, you are running two different processes and they are sharing the cache, right? So let's say you have this core 0 running process 0, and you have core 1 running process 1. And they have their own, actually L1 cache is inside the core, so I'm not drawing it normally. And then L2 is normally shared, okay? So let's say the L2 is shared, okay? So let's say when you run, what happens is, let's say our process P0 is a attacker, and it wants to learn something about process P1, okay? So now, before I talk about how the channel is constructed in this particular example, we know what is the purpose of L2 cache. The purpose of L2 cache is to speed up the memory accesses or access to the data and bring it closer, right, to the cores. So now, but they are, both of them are sharing the cache now, right? So let's say there is some particular, do you know the internal organization of cache? Like, do you know what is how to say, what is a way in cache and what is a set in a cache? So here, let's say the cache is organized in rows, okay? And each row is called, I'm just trying to make it simple. Each row is called a way, okay? Let's say this is way 0, way 1, and so on, okay? And then each way is divided into sets. So like, this is set 0, this is set 1, right? Okay, and let's say now your process P0 is accessing some data. So now the data is mapped into sets. It is brought from the memory and put in the cache, but where in the cache? It depends upon the address of that data. So and basically what happened is that you look at the address, some particular bits of the address, and use those bits to do the mapping from the address into the where it goes into the sets. Okay. So let's say all the addresses odd level, even level, we look at the last two bits of the address, B0 and B1. And if it is a even number, the last bits will be 0, right? Let's say for those addresses which have the last two bits equal to 0, all of them go to same way 0. Like, let's say, can I give you an address 0? Then address 1 will have not address 2, so it will be like 1, 2, 4, right? And 1, 2, 4, and then maybe also address 8, right? All of them have last bit equal to 0. So if I have data located, A located at data X located at 0, Y at 4, Z at 8, all of them will be mapped into way 0, because let's say, and then 0, 1. Okay, we are checking last two bits. Similarly, if you look at the address, like let's say 1, and not 2, not 3, and then 5, right? So it will also have 0, 1, and then 8 and 9, right? Everyone is with me, or I'm wasting my time? If you don't understand, stop me, okay? I'm just trying to explain how the data is mapped, and then I will come back to your question, how channel is built, okay? So now let's say process P0 runs and it reads its data, and it turns out that its data, which it reads, is XYZ located at addresses 0, 4, and 8, and all of them map here. So, okay, X is mapped here. So when it reads Y is mapped here, but in the same way, way 0. But it has only two sets. One set is already occupied, so the Y goes here. Okay. Okay, let's say then after that, it stops its execution. Why it stopped execution? Maybe it was like sleeping, put to the sleep mode, or something happened. So then P1 is also executing. Now what happens is that P1 also starts the execution, and it also reads its data, okay? And it also needs to map its data into the cache, right? So they are sharing the same cache. Now, all those addresses which map into this way, they will overwrite the already available data like X and Y, right? Let's say the data read by P1 is Q and J, right? But let's say it reads only one. So it overrides J, overrides X, okay? Now when after that P0 comes back and it wants to try read X, its own data, it was expecting that it will have a hit in the cache because it already had placed the data in the cache. But now the data was overwritten. It is not there. So it has a miss, right? So it was expecting a hit, which means it was expecting that I will be able to get data in less amount of time. When it is a hit in L2 cache, it takes almost 10 clock cycles. But if it is a miss, you need to go down to the memory, and which takes 100 cycles. So it measures, okay, I was expecting 10 cycles, but no, it took me 100 cycles to get the data. It's mean that when I was not running, another process was using the same set, and the data, so it gives me one information. I got some information about the victim process. What? That it is using this, its addresses are also getting mapped into the same set, same way, and like same set. And there was data left over by that process, the victim process. So now how the channel is, coming back to your question, how the channel is constructed. Cache was initially, the purpose of cache was to speed up the execution. Its purpose was not to leak the information, any kind of information, okay? But now it is leaking information to P0. What information? It is telling that, okay, another process, addresses of another process are also getting mapped into the same way 0. And when you come back, the data of other process was there. Because if it was not there, I should have been able to get my X in a lesser amount of time, 10 cycles. Okay, now you get the idea how channel is constructed. So it is not like you are building new hardware, or so it is a combination of both things. You have the existing hardware, but you are using it in a way which was not intended to be used, right? Yeah.
So in this example, could the attacker processor just set up like dummy data in the cache and just wait to see what other processes do in that cache?
Say it again, sorry. I was thinking that maybe other students also need to participate, so that's why I couldn't focus on your question. Yes, go ahead.
Could the attacker processor just say like, write X, Y, Z, W, and just wait to see what another process does? And just...
Yeah. Actually, this is what you said is the basic idea of an attack, which maybe we will cover in our paper, the detailed attack. Here we are not covering any detailed attack. We are just talking about the high level picture. Okay. Any other questions?
Is this the same sort of like logic they use when for process injection attacks where they're like taking over the memory address? Is this like is that like the same architecture that they're using the same hardware, or is that just in the RAM?
Can you more elaborate a little bit about
Yeah, so like process injection, where it's like you run a process and you have another process that overrides into that memory where that one's gonna go. So that way when you run, that one's actually running a different process. Is it using like channels like this in a similar way as like you were describing there with P1 overriding the thing to J and then P0 accessing it, and then instead of missing, it actually runs.
Okay, I got it. So the idea of the injection attacks is like basically I'm an attacker, you have your data, and what I want to do is I want to corrupt your data by overwriting, okay? Or by tampering with your data, okay? Here, we are not tampering. The attacker just knows based on the timing that the same set was used by another process, okay? And it cannot actually fool the process P1 in this case, or victim process. Here, it cannot fool the P1 by modifying, let's say, its data from J to J prime, and then fool it that, okay, this is my clean data. No, because when the process P1 will come back, it will see that this is dirty. And now how it works, how we find out that whether a cache, this is also known as line. So how we find out whether a cache line is dirty or not is a different question, because there are hardware mechanisms to detect it. So when I will see that it is dirty, I will not use that data. Okay. Any other questions? Okay. Okay, so so we had a very brief introduction about about channels and about the information leak rate or information leakage rate. So for those who have read the paper, can you tell me what will be the characteristic of a strong or impactful attack? One, we have also mentioned it in the start of the lecture. First characteristic would be that I make no assumptions about the weaknesses of the victim or about the capabilities of the attacker. So for example, I make no assumption that attacker and the victim process are co-located on the same machine. So if there, let's say there are two attacks, one which makes this assumption and other which doesn't make this assumption. So then definitely which doesn't make this assumption that two processes are located on the same machine is stronger and more impactful, right? Because it has more power, even if they are not located at the same machine, but they are connected by internet and they are doing something on internet, maybe there is no direct communication, but still I can launch that attack, right? Second, we will consider attack impactful or strong, which has higher information leakage rate, right? Why? Why it is important to have the capability to transfer higher amount of information from sender to the leakage in a given amount of time. Let's say one attack can transfer 1 kilobyte per second. Other can transfer I'm just making up some number, 10 kilobyte per second between sender and the receiver using a Covert channel or side channel. So we will say the second one is more stronger. Why?
Faster exfiltration rate? The faster exfiltration?
Yeah, but why faster exfiltration is important? Why?
Avoid detection. Avoid detection.
Yeah, one thing, yes. So the thing is let's say if you are transferring the information, but to make any meaningful, you are transferring the data, but make any sense out of that data, you need to have a minimum amount of data, let's say 100 kilobyte. Now, if first one is transferring only 1 kilobyte per second, it will take 100 seconds for it. But the second one is transferring 10 kilobytes, so it will take 10 seconds for it. So in the first case, it will take longer time to succeed for that attack to succeed. And if it takes longer time to succeed, it means that there is more opportunity for any defense mechanism, if it is deployed already there, to detect the attack and to take any, protection mechanism, to trigger any protection mechanism. Okay. So that's why it is higher that information leakage rate means more strength, more powerful is our attack. Okay, what about impactful defense? Let's say if I have one attack and to protect against the same attack, I have two different defenses and I need to compare them, which one is better. So what should be, sorry?
Detection speed should be a variable.
Yeah, yes, one reason, yes. That how quickly you can detect, how long it takes. Let's say the attack has launched at time T1 and the defense mechanism A detects it after 10 seconds, and the other one B detects it after 5 seconds. So B is powerful. Other than that, any other thing? Yes.
If it's preemptive, it can defend before the attack happens, or it can detect.
Yes. Yeah, that definitely makes sense. There are different kind of protection mechanism or defense mechanism. One is prevention. You take action before the attack actually happens. Second, you do the detection, which is you allow the attack to happen, but then you focus on detecting it once it has started. And third is like rolling back. You detect it and then you roll the attack back to undo its effect. Okay. Yeah, okay, so these two parts I haven't written in my presentation. Go on. Which means there is something else also, right? Okay, so when you think about the overhead of defense mechanism, there is no free lunch in this world, right? Okay, yeah.
So whenever you're thinking about like a better defense, don't you have to also like think about the hardware aspect? Because they're attacking the software, but you also have to think of a hardware aspect that they're trying to get. So don't you have to like have more defense on the hardware part and the software components? So like saying your hardware has to be good without it then like impacting it.
Yeah, I think what you are saying is relevant, but it is on a different direction in the sense that how you are implementing your defenses is implemented on the hardware level or on the software level. Definitely, there are trade-offs when you implement on the hardware. It takes less latency, less time, but then it is rigid. I mean, you cannot modify your defense, you cannot update your defense as compared to the software where you have more flexibility. If you later on want to make changes or improve your defense, you can easily do that as compared to the hardware-based implementation. But okay, let me state it. So the third is like, if you are implementing your defense, it will definitely incur some overhead. And overhead is like in terms of maybe it slows down the execution of your applications or your workload which you are running on the platform, right? Or it affects the latency of something. So an impactful defense will be one which has minimum or ideally zero overhead, which is not possible. But lower the overhead, more strong is your defense in terms of performance. Okay. Okay. Oh, I should have dragged this figure. Why it is looking like that? Okay. Anyway, let me make the correction now. Yeah. Okay. Okay. So classification of side and covert channels. Okay. So we have talked about channels, right? And how they are built in the sense like how you discover them, right? But then we can classify into three different categories. One is timing based. Timing based is basically where your attacker is trying to do what is like look at the timing difference of different operations which are performed by the victim. So if there is difference, okay, even before going into this discussion, if there is a data where there is no how to say no all if you have data set where all the data elements are same, right? You cannot extract any meaningful information from that, right? But if there is variation in data, then you can make some inferences from those variations, right? Okay. In the same, so in the context of microarchitectural based side channels or covert channels, if there is no variation in anything, it means it is super safe. But if there is variation, then it means that we are leaking the information. So timing based channels, what do they do is that in these cases, our attacker looks at the timing difference of different operations which are performed by the victim, and then based on the difference in timing, it tries to make some inferences. And as a result, it can get some information about the behavior of the victim, what the victim is doing. Okay. So, for example, let's say you have two processes running on the same machine. Process A, in one case, let's say in first scenario, process A performs lesser number of memory accesses. Both are performing memory accesses, but we are not changing the number of memory accesses performed by process B, which in this case is, let's say, is victim. But process A is the attacker. In first scenario, it is let's say in the given amount of time, it performs 10 memory accesses. But the memory accesses performed by B, they are fixed, okay? So, and then it looks when it performs 10 memory accesses, in the meantime, it measures the timing of memory accesses performed by process B. And then later on, in a later stage or in a later phase, what it does is that in the same amount of time period, it performs 100 memory accesses. And then it looks or tries to monitor the timing required by the memory access by the process B to complete its execution. And it sees that there is significant difference. Why there is significant difference? In two cases, 10 and 100. When process A is doing 10 memory accesses and 100 memory accesses, and it measures the timing required by process B to its complete execution, and it sees there is significant difference. In first case, it is lower. In second case, it is higher. Because both are doing their execution, though both are performing the memory accesses, and memory is a shared resource. So there is competition or contention among them to perform accesses to the memory. Now, if process A performs higher number of memory accesses, it increases the level of contention. And as a result, the execution of the process B slows down. So its timing is affected. Timing of the process B is affected, okay? Access-based channels are those where actually attacker tries to directly access some information. Instead of like, in the first case, the attacker was focusing on measuring the timing of the victim or some operation performed by the victim. But here, it directly tries to access some information. And as a result of accessing that information, yes, definitely the timing of the victim is affected, but the prime motive or prime first step is to access some kind of information directly. So I already gave you an example. Okay. So you access your own data. Here, process P0 was accessing its own data, right? And as a result of its accessing its own data, what can happen is that timing of process P1 can also get affected. How it can get affected? Because now it knows, let's say, that some addresses of P1 are also getting mapped into the same, same way. So it can, let's say it says, flush this whole way. Flush mean remove all the data. So next time what will happen that when P1 will come, it will take more time for it because data is gone and it needs to be brought back again, right? Okay, trace-based, these are the side channels or covert channels which rely on measuring program execution. And for that, I already gave an example. Let's say if you're doing the heat scanning example. So what happens is that for this kind of attacks, you need the physical proximity. So that's why these attacks are not covered trace-based such as side channels or covert channels. They are not covered in the paper, but this is how you can categorize them. Okay. So again, and here is the depiction of how we can categorize them. So channels, we have three types of channels: timing-based, access-based, and trace-based. But trace-based, they require the physical proximity to the victim. But that's why we are not covering them in this paper. And then you can divide these channels, again, like a timing-based channel can be both an external timing-based channel or an internal timing-based channel. And access-based, it is internal timing-based channel. So what is meant by external timing attack? Can anyone tell me?
So they're basically looking at the victim at the same time. So they're monitoring the victim as well as monitoring themselves, making sure that they're going at the same processing times and making sure they're not getting caught.
Yeah. So in external timing attack, what happens is that the attacker measures the timing of operations performed by the victim. But on the internal internal timing attacker actually looks at the timing information of the operations performed by itself. For example, here it was looking at tried to access X, and it was waiting, like expecting that it will take 10 cycles, but it took, let's say, 100 cycles. So, but it was measuring the time, but it was measuring the time of its own operation, not the operation performed by the victim. Okay. Okay. Okay, Okay, how many of you are familiar with this figure? What's going on in this figure? How many of you know or like understand, let's say 70% of it? Or how many of you are seeing it for the first time? Okay, so actually, this is a general diagram for a typical two-thread SMT processor. SMT simultaneous multi-threading processor with 5-stage pipeline. I have highlighted them so that I can explain. I don't forget to explain them. So when we say two-thread and simultaneous processor, it means that it is a kind of processor which allows two threads to be executed at the same time. And how many of you now want me to explain threads? Or I can assume safely that you know what a thread is and how it works. So thread is a stream of instruction. So like, if you have, let's say, programs, you have a program and you write code. And let's say I can ideally, in ideal world, I can break down this program into two sections such that they are independent, which basically mean if I start executing from here, I can ask one thread to start executing from here, another from here, and then there will be no dependency. Then okay, what I can do is that this stream of execution, I will name it as thread 1, and this stream of execution will name as thread 2. Okay, so this is like very how to say high level explanation of what thread is. But definitely, if I want these two stream of executions to be executed at the same time, a stream of instructions to be executed at the same time, it means I need two different hardwares, right? Because the way will they run? They will run on the hardware. But if the hardware can support only one stream of instructions to be executed at one time, I cannot have two threads, right? So that's why that in a two-thread simultaneous multi-threading processor, what they have, that they have a pipeline. I will come back to pipeline later, but what do they is that they duplicate the pipeline. So you have this one pipeline on the front and the second on the back. Like you have one instruction fetch stage here, one in the back, decode, memory, but execute is shared between the two pipelines. Okay. So one thread will run, let's say, on the pipeline on the front, and the second will run on the, which is on the back side, shown in the figure. Okay. So that's why it is called two-thread and simultaneous multi-threading, because both can run simultaneously. Both threads can run simultaneously. When you will have, let's say, 4-thread simultaneous multi-threading, then you will have 4 copies of the pipeline. Okay. Now, let's talk about the pipeline itself. So pipeline, basically what you can do is that you can have a processor which has no pipeline, which is like you give an instruction, the whole instruction is first executed in a single step. And then after that, the second instruction can execute once the first instruction is done. It is just like, yeah, I can give you an example. Let's say you have a machine, which is washer dryer in a single unit, single machine, okay? So if I put my clothes, dirty clothes to wash, so first it will wash them, then it will dry them, then it will become empty so that I can put the second bucket in, right? But it will take more time because it is also doing washing and drying, both things. What I can do it, I can break it into two. This is washer, this is dryer. Okay, so I can put my first bucket here. So when it is done, I can move it in the dryer and I can put the second bucket in the washer. Okay, so now what I'm doing is I don't need to wait for second bucket to be put in for a longer amount of time. I only need to wait for this amount of time, which is T by 2. If this is 2, this is T, this is T by 2, right? So in the pipeline, so they do the same thing. What they do is that the execution of an instruction, they break it into multiple stages. So just like we broke our washing process. So, and first, what they do is that they access the memory. Why they access the memory? Because the instruction you want to execute, anyone want to tell me why we want to access the memory in the first step? Where are instructions located at the start of the world? Where are the instructions located? in memory. So if I want to execute an instruction, I need to read the memory so that I can fetch the instruction. So I fetch the instruction by accessing memory. I'm not going into detail because it will take 2 lectures to explain if I want to explain this whole thing in detail. But anyway, you first fetch the instruction from the memory, which you need to execute. And then this is the first stage. In the second stage, based on the instruction, you decode the instruction. The instruction you have fetched, you decode it. Decode means, yes, you have fetched the instruction, but how I know what to do with this instruction? Is it an add instruction or multiply instruction or some logical instruction? So I don't know what to do. So I decode that instruction to find out what operation it needs to perform. Okay. So here I'm doing decoding. So after decoding, I need to maybe read the registers. Most, not maybe, like, yes, I need to register read register 99% of the cases. So, which basically, let's say if it is an add instruction, so maybe I need to add 2 registers and put result back into the 3rd register. So I need to retrieve those source operand registers. So that's why I'm decoding the instruction and then I'm reading the register file, and whatever I get from the register file, I cross it into the next stage, which is the execution stage. So once I know what type of and here there is control, which is basically telling here, okay, what registers to read, and it is also telling the execution, the same signals are passed to the execution stage to tell, okay, you have this data coming from the register, but now what to do with this data? You want to add these 2 numbers, or you want to need to multiply these 2 numbers? Okay. So here we are doing the execution. This is the execution stage, and once the result of execution are ready, we move to the next stage. And in the next stage, maybe the results you have generated, you need to write them in the memory depending upon the instruction. Like if it is a memory access instruction, you need to write the data in memory. But if it is, let's say, arithmetic instruction, the result is written back in another register. So here you write the result if needed to be written in the memory. If not, the result is then sent back to the register file. Like let's say if you said add 2 numbers, and that is where to put the result, in memory or the register. If you say in memory, it will be written here. If not, the result will come back and put in the register file. Any question?
So it's kind of just like thinking about like the way the threads were working earlier. So if you have like threads where if they're each running your own process, that's like a multi-step process, could say thread 1 is like halfway finished with it. So it's done some steps up here and there's data that it's been writing up here and it hasn't sent it to memory yet. Can thread 2 access any of that, or does it have to wait until it's written to memory?
You are making life very complicated. You are assuming there are dependencies between threads, right?
Yeah, or like in some architectures.
Yeah, that definitely there is, but I would just want to keep it simple. So if there are dependencies, then you cannot write the data in memory until, let's say there is a dependency between thread 1 and thread 2, which basically means, let's say thread 2 consumes the data, which is generated by thread 1. So now thread 2 cannot continue execution until the data it needs is ready. Okay. So, but if we wait, let's say if thread 2 reads the data from memory, but if we wait for the data generated by thread 1 to be written in memory, and then thread 2 can execute, it takes too long because it is expensive to access the memory. So then there are mechanisms where you don't write the data in memory. Before writing the data in memory, you allow thread 2 to proceed, but later on you update the memory. Okay. So you still maintain the dependencies, but you optimize the execution. Okay. Any other questions?
Yeah, just a quick follow-up on that. So if it's trying to access something from, like from thread 1, but thread 1 got stuck somewhere, would thread 2 also be stuck waiting until that data is completed in thread 1, or would
let's say thread 1 is
just crash out and
let's say thread 1 is terminated or killed, then what will happen to anyone who want to answer who has taken the OS course?
What's the question?
Let's say you have thread 1 and thread 2, there is dependency between them. So thread 1 is producer, thread 2 is consumer. They are running on at the same time, but then thread 2 needs data from thread 1, and thread 1 is terminated because of some reason. it is killed. Now, what will happen to the thread two?
This is just a deadlock situation, right? Or depends on how the resource management is and.
Yeah, so you need to have a mechanism or policy to handle this kind of situation, which is, for example, in this case, maybe you will, what you will do is like, you will allocate a time, okay, if a thread doesn't respond within this time period, so you set a timer. And if a thread doesn't respond within this amount of time, you decide, oh, this thread is terminated. And then for thread two, you either have to notify the thread two or maybe in worst case, kill the thread two as well. Okay.
And then,
So there should be some, like, basically the main important thing is that you need to have a mechanism to identify this kind of situation or detect this kind of situation.
because if you didn't have that, it could just like slow down the whole system, which would make you vulnerable.
Yeah, it will be like, it will be stuck. And since it is not making progress, the pipeline will not be occupied by some other thread. So that's why you need some mechanism to take over that thread which is stuck. Yeah. Okay, any other question? Okay. I've quickly explained what a processor pipeline is. Okay, stateful functions. Okay, before going to stateful functions, so I want you to like focus on understand here that this in the execution stage is shared. It is not duplicated between the two pipelines, which basically means that the thread which is executed on pipeline one and the pipeline two, when both of them want to execute some arithmetic logical operation or some floating point unit of floating point operation, they use the same functional unit. Okay, why? If we are duplicating everything, why we don't duplicate this one?
More expensive. Have more ALUs and.
Yeah, okay, one reason, but that is the reason for not duplicating. Okay, not duplicating. What is the reason for sharing? I know they are like very closely related, but I'm trying to give me a reason which focuses more on sharing, not duplicating. What you said, I understand, that's correct. It will increase the cost. It will increase the cost, it will increase the area, it will increase the power if you duplicate.
So you don't waste resources.
Yes, because in one execute stage, you have multiple functional units. Like here, they have shown two floating point unit, arithmetic logic unit. Maybe you have a multiplier separate. So if two threads are running, what happens is that many times it happens that both of them are not using the same functional unit. Maybe one is using the floating point unit, the other one is using the arithmetic unit. So it's fine, you can share. But it can also create a problem in the cases where both threads want to access the same functional unit. Let's say both of them want to perform an addition instruction. Addition. So in that case, there will be a contention, right? Okay, stateful functional units. So, state basically mean that you can store some information about your previous history. Okay, so for example, memory access, it is or memory, let's say itself. Memory is itself a stateful component. How it is a stateful component? Because when you want to access the memory, what happens? You provide an address. On the output, it will give you data, but the data provided to you for a given address depends upon what you had stored in the previous time, right? And once you write the data, you change the state of that memory component, right? Similarly, register is a stateful component. You give the address, it gives you the data, and the data you get on the output depends upon what was stored in the past. Okay, register file. Floating point units, arithmetic units, I'm not sure, and I don't want to make a wrong statement, but I'm not sure if we can consider them as a stateful component because here I'm assuming that they don't have any storage component here. Whatever, they are just a combinational logic. How many of you know the combinational logic? Combinational logic is one which have no storage capability. Whatever is on the input, you apply some kind of processing on it and give the output. Okay. We have 2 minutes before your submission starts. And the pipeline we have considered here is an in-order pipeline. In-order pipeline mean like if you have, let's say two threads are running. So this is instruction 1, 2, 3, 4. So all these instructions will be executed in order, and the results they generate, they will be updated in the memory in order. Okay, but sometime in order execution can have performance over Hrdwr. It can slow down the execution. So we can optimize it if we allow the out of order execution, which basically means like, let's say there are two instructions, 1 and 2. So instruction 2 is not dependent upon the result of instruction 1. So I can, and instruction 1 is waiting for some data to become available from memory. I can allow instruction 2 to go ahead and execute instead of waiting for instruction 1 to complete and then. So I can allow it to execute out of order, and as a result, I will avoid the waiting time for instruction 2. Okay, but again, the results generated even in the out of order execution, results generated by instructions, they are committed in memory or written in memory in order, in program order, same order. So first the results generated by instruction 1, they will be written, then instruction 2, then instruction 3. Although instruction 2 was allowed to execute earlier. Okay, go ahead. I think your submissions are open. You can go ahead and fill the class participation form. You have 15 minutes. You don't have a laptop? Okay, so if you have laptop, try to bring it because that is more convenient for me. Next time when I will be evaluating your work. Anyone else who needs that part?
I have a laptop, but for Sophia's 2 questions, but I put them both under question 1. I have a laptop.
Okay, you can just number them 1 and 2 if you want.
Okay.
You can
Or
just
like I
number
can put
them
it in
1
1,
and
or should I just put another one in like the?
two. No, you can put under the same field,
the same.
but just number them like 1 and 2. Yeah, you can fill it and then give me in 15 minutes.
So these are asking about the papers for the.
No, whatever I have talked about. Yeah, so I mean, if you had any question, any comment, so actually this is to encourage the class participation. Okay, so I don't want to disturb you while you are doing that, but the person who is presenting on Wednesday, please stay here after the, okay. Okay.
I probably should have asked this, when we were going over it, but for the out of order execution would there be any reason why, 2 wouldn't be able to go above 1? Or what's the special cases for that?
Ask again.
For the out of-
Special cases for what? For doing out of order?
Yeah, out of order, like, can that happen all the time?
No,
Or
not
what will
all,
block it, or what will allow it?
not all the time. Let's say. Let's say this is initial state. In register 1, I have data X. In register 2, I have data Y. And then I have some instruction 1. It says bring data from memory, some address from memory into register 3. Instruction 2 says add R1 and put that in R4. Okay. This takes 100 cycles or more than 100 because accessing data from memory is 100 cycle, and then on top of that cycle for executing the instruction. So at least 100. But this, if we already, this was the initial stage. If you already have data, it will take only 1 cycle. Okay. Now, one option is that I wait. So one option is that instruction 1 starts executing here. Then 100 time cycles are passed. Then instruction 2 is executed. And here we have time. And this is 1 cycle. Here time is increasing. Okay. And then let's say after this, we have also other some instructions, okay, which are not dependent on this one. Okay. So now I too need to wait for 100 cycles. Why I'm making it wait? I can, it has no dependency on the previous instruction, right? So what I can do is like, okay, I can allow instruction 2 to execute. It will complete in 10 cycle. In the meantime, I can start this one. I can start this one, and then after starting this one, I allow, okay, I2 to go ahead. So basically, which means that it will start after 1 time cycle. So this is like 1 cycle. Like after that, I've issued, I release this instruction. In next one, I can have the instruction 2. So it waits only for 1 cycle, not for 100 cycles. Okay, so coming back to your question, is it done all the time? No. When you find out that there is an opportunity for doing the reordering, let's say if you have 100 instructions, and let's say I just want to change it. Now I cannot reorder. Right?
It's dependent on it.
Yeah.
Yeah, okay.
Could a process still have more than 2 threads?
Would a processor.
Yeah,
Processor or
a process, could it still have more than 2 threads in this architecture, or is it limited to?
Okay. So the number of threads, software threads and hardware threads is different. So you divide your program or a process into threads, but then you need the hardware support for them to run on, right? So like, let's say if you divide your program, you create 4 software threads for your process. And your hardware supports only 2, like in this case. So then you cannot run all 4 of them at the same time. So then you need to do scheduling. Like maybe you say, okay, I allocate this fixed amount of time for each thread. Let's say 10 time units. So 10 time units for first 10 time units, T1 and T2 run on this one, and then next time 10 time units, T3 and T4 run on. And then you keep changing that. They keep taking the turns like one after the other. But you cannot, like, if you want to run 4 of them at the same time, then you need your whole hardware to support it.
Path, just because I was wondering, like, when I was reading the article, it was saying about like the faster and the slower paths, and what, like, this kind of more from my understanding, like why, when you're have your both when you have the fast and the slow, you would go for the slow just because you're not trying to overdo and miss the data that you're trying to leak out. Is that why you're going for more of the slow path instead of going for the fast path?
No. So it is not like you can decide whether you want to follow the slow path or fast path. The program cannot decide. But what happens is like, a slow path and fast, it doesn't mean that these two paths end up in the same result, no. The focus is on their timing, how much time they consume, not about they are doing the same thing. They are not doing the same thing. But when we say slow, it is slow, but it may be doing operation one. And fast, it is fast, but maybe doing operation two, not the same operation. Okay. So the focus is on timing. So here is now like a more concrete example. Let's say if you have two instructions. First is add instruction. Now, if you execute add instruction, you first fetch it from memory, then you decode it, then you execute it here. So which is doing the addition, adding two numbers. Then writing the result either in memory or back into the roster file. Second example is that let's say multiplication. Again, you read the instruction from memory, you decode to find out it is a multiplication instruction. Here you perform multiplication, you write the result in memory or in the register. Everything else is same other than what is happening here, right? So here in one case you are doing addition, in the second you are doing multiplication. Addition is much faster, it takes 1 second. Multiplication, like in typical case it takes 1 second. Multiplication, it is much slower as compared to the addition. Now if I am if I look at the execution time taken by the two instructions, one takes the fast path and one takes the slower path, which is through the multiplication unit. So that is what they are saying, fast and slow paths. So these fast and slow paths, they appear during the execution of the code.
So going back to the example on the board, so my understanding is that a buffer memory overflow attack needs to make the victims process leakage, leak the memory addresses to calculate the offsets and inject a payload. So is that possible using a side channel kind of thing?
Buffer overflow, it is a kind of memory attack, but it is not the focus here in this example. So in buffer overflow, what you basically do is, let's say you are writing a program and you ask any person who uses the user of the program, you ask them to enter the name. And in your program, you specify a field or a string to take the input, right? And size of that string is, let's say, you set it to 20. You assume that the longest name is 20 characters. And I am the person who is giving the input. And I write my name, which is Navidu Mustafa. So it takes 40 characters maybe. Okay, or more than 20 anyways. So what will happen? The data will be written into the memory, into your that variable of string, but it is only 20. So 20 will be written and remaining 20 will overwrite the memory, which was not supposed to be written. So now your buffer, which was supposed to store the 20 characters, is overflowing. And as the result of that overflow, now it depends. If I, instead of 40, I give 1,000 or 10,000 characters, I can write 10,000 bytes. Maybe those bytes are in the heap section of the memory. And then are maybe in the stack section of your memory. So if I can overwrite stack, if I am able to overwrite stack, I can develop an attack which can take control of your program.
But there's secure mechanisms like the address space randomization, where the program is executed in a different space.
There are many protection mechanisms. ASLR or address space layout randomization is one of them. But then actually, I will try to cover this paper, which is about eternal war in memory. So the title of the paper is Eternal War in Memory. So where basically attackers develop an attack, defenders develop a defense. Attackers develop a new attack which breaks the defense. They develop another defense. And so this is a never-ending war. So for like ASLR, it is one of the mechanisms, but then there are other attacks which can break the ASLR. Okay, everyone has submitted. So do you think you need 10 minutes or 15 minutes for submitting the class participation form? It will give me 5 more minutes if we can reduce it to 10. 10 will be okay? Okay, so next time we will then make it 10 minutes, okay? And okay, one more thing. For reading notes, I will make it an announcement. I am going to make it a requirement that you have to upload your annotated PDF of the paper. Like when you are reading it, you are making notes, you are highlighting something, whatever. Okay, so upload it so that I can see, okay, you have read the paper. Thank you. I will upload the slide. There is some material which I was not able to cover, but go ahead and try to look at it on your own, especially the one who is going to be a discussion lead. You are going to be the discussion lead, right?
Oh, for the first one?
No, you, okay, okay.
That's
You're
Course registration. Form.
This one?
Course registration form.
For this course, right? So you can come to my office in 15 minutes. I will be in my office.
Thank you.
Okay, your name is Saeed?
So
Okay. Oh, I forgot to take the attendance, but everyone who has submitted the class participation form has attended, okay. Okay, so do you have any questions about the paper? You are going to be discussion lead, and I want it to be a very impactful, meaningful learning experience for everyone. So do you have any questions?
Not at the moment. I've only got to section 2 of my first pass.
Okay,
I'll read the rest tonight.
okay.
I might have better questions tomorrow.
Okay. Have you covered section 3 or not yet?
Not yet. I just finished section 2 before
Okay.
class.
Okay. So. Okay. Do you have time? Are
Right
you
now?
Yeah.
Mm.
Okay.
Should have some time.
You have some time. Okay, so maybe I can explain this to you. In section 3, they are basically talking about, in section 2, they are saying that the main problem, you can take the seat if you want. So the main problem is that various components in the processor, they are shared among processes, right, for execution. One thing is that one problem is sharing. And second is that there are fast and slow paths, right? Just like I gave you an example. So these are and based on fast and slow path, both of them actually result in timing difference. If you take a fast path, it will take less time. If you take a slow path, it will take more time. And similarly, if you are sharing the components, then there will be contention. So if there is contention, then there will be timing difference. And not only that, but if you are sharing components, you can use the shared component to affect the execution of another process, right? Right. So here, this is an example which they have mentioned that how a stateful component, output of stateful component can be, one process can affect it such that, let's say not affected, it can try to manipulate it in such a way that it can affect the execution of the other process. Okay.
For stateful component.
Yeah. So, and they gave an example of a predictor. Okay. But they didn't talk about particular predictor. They just talked about like in general terms. Okay. So to make it clear, I can just try to explain the example to you. So this is named as Pad predictor. Okay. So what they do here is like, you know how why prediction is needed?
Why what?
Why prediction is needed? Branch prediction is needed.
Oh,
you know?
Right, for the. I'm trying to remember.
Okay, like
for the if else, right? To know, like whether you should go into the
if branch or the else branch, where should I go?
Yeah.
Okay. So like And in like typical case, let's say traditionally what I need to wait is like need to wait for the condition to be executed to find out whether it is true or false. But if I wait for it, the condition will take time to be completed, execution of the condition. So, and this will slow down my process, my execution. So what people say, okay, we can predict whether it will be turned out to be true or not. So let's say, if condition is and else. Okay, so instead of waiting for condition to be, this is an instruction definitely, to be executed and completed, and so I get the result back. Instead of waiting for that, I can do it. I can predict, okay, I predict that it will be true. So then I will start executing this one. And then when the result of the condition is available, I check whether it turned out to be true. If yes, no problem. If false, then the instructions which I have started executing from here, they are in the pipeline. I need to flush them. Right? So there are different types. So how the prediction itself happens. I said I can predict, but how I can predict? For that, there are different kind of branch predictor designs.
Is this similar to, when you do the Boolean check where you kind of predict, not check, but if your condition is like, if this and this or this, you only check the first part, like if the first part is false, you just know you can skip the condition? I don't know if that makes sense.
No, because if let's say this condition is false, then you need to go here.
Yeah.
Or maybe it also has its own other condition, else is condition 2.
I think what I was referring to, like if in your first condition, right, if condition 1 is say something, if statement 1 is true and statement 2 is true.
No.
Right.
I understand what you are
But
talking
you
about.
don't check-
You are talking about short circuit.
Yeah, short
and-
circuit.
Yeah, short circuit operation, and no, this is not the same thing. Okay, but as even in short circuit, you have to at least check one first instruction. You will, let's say if it is false and everything else is and state condition 1 and condition 2 and, but first is false, don't need to check it. But even then, you have to at least check condition 1, and it takes time, right? So
here
we
you're
don't
just-
want to wait even for condition 1. We don't want to wait for execution of condition 1. Okay, that's why we are predicting whether condition 1 will be true or false. Okay, but now how we do the prediction, for that there are different kind of hardware predictors. This is one of them. Like, you want me to explain this?
Yes.
Okay. Okay, so in hardware, in this predictor, what they do is that for every address, every address of every prediction conditional statement, they keep the address, and then for that address, they maintain the history. Even before that, do you know how 2-bit predictor works?
No.
Okay, I'll share these slides, and I will share a video, and I will also share, okay, watch this, that is a big video, like 2-hour video. I will just share like, okay, watch this from this point to this point.
Okay.
Okay, but let me explain only how 2-bit predictor works, because that is they build this on the top of 2-bit predictor. So 2-bit predictor is like, you just have a 2-bit counter, right?
Right.
If you have 2-bit counter, what are the values you can have?
This is
0, 0, 0, 1, 1, 0, 1, 1, right?
Right.
So what they do is like, they define them as states. Okay, so let's say if there is a conditional statement, and my counter is initially when I start the system is at this state. So if it has value 0, 0 or 0, 1, I will predict that it will be not taken, the branch will be not taken. And if the counter value is 1, 0 or 1, 1, I will predict that the branch will be taken. Now let's say I start my system, my counter has this value.
And this is for the
2-bit.
program counter or just?
No, not
to the counter.
it is simple 2-bit counter,
Okay.
not program counter. So I have this counter 0, 1. So I maintain this for the address of this instruction. Let's say address of this instruction is A. Okay.
Right.
So I have a counter for this address. So whenever I have an instruction to execute at this address, I check its corresponding counter. And let's say the value of counter is 0, 1. So which means I'm predicting that branch will be not taken.
Okay.
Okay, which means that I start executing here. Right?
Okay.
Okay, but then condition is anyway executed. So when condition is executed, its actual results come back, becomes available. And then I check whether it was actually taken or not. So let's say if it was taken, so I change my counter to 10.
Ah,
Okay. Now, next time, when again, let's say there is a for loop. Okay, next time when I execute, when I again at that address, I check, oh, now that address value of counter is 10. It's mean this time taken. I'm predicting it will be taken. So I start executing here. Okay, and actually it is taken. Okay, so I again increment the counter. So I'm like again, but I'm in the same region. I'm taken it. Okay, and let's say again come back and it says, okay, 1 taken. So I saturate, I don't increment, it saturates. Actually, it is called 2-bit saturating count. So it cannot go up from 1, it cannot go down 0. Okay. So here I will keep predicting taken. Now, let's say next time I say again condition, and here value is 1, I say taken, but actually it was not taken. Condition done. Let's say this time every time I'm checking from input from user, some input from user and my condition with that, and it was not taken. So I decrement the value of counter. Every time the branch is actually taken, you increment the counter value. Every time the branch is actually not taken, you decrement the counter. But the prediction you make, it depends in which region the value of the current value of the counter falls. If it falls in the upper region, you predict taken. If it falls in the lower region, you predict the not taken. And every time after you make the prediction, you compare it against the actual value. If it is taken, you keep incrementing. If it is not taken, you keep the actual value. If it is not taken, then you keep decrementing. Okay, and they use it here, the 2-bit counter.
and this state is saved for each instruction or just
Each address where each branch address.
each branch? Okay.
Yeah, each branch, like here you have a conditional variable. So every address which corresponds to a branching instruction, for that you maintain its own 2-bit counter. So it is not like 2-bit counter for all the branch. No, one 2-bit counter for every branch instruction.
Right.
Yeah. And I will have uploaded these slides anyway. So you can look at them and I can send you the link of the YouTube video and specify, okay, watch this from this time.
This might be more work, but could you have, say, another thread that keeps a state of taken and one for, like you do both, like states in the branch?
Say it again, please.
So like instead of keeping track of what's taken, not taken to make your predictor, you have another thread, which might be more overhead, that does the work of inside the if, and then one that does the if else, and then depending on what the actual result is, you just take that. Work.
Yeah, you are saying that let's execute both of them.
Yeah.
Yeah. Actually, I have not read, but I'm sure there are papers which take this kind of approach. But at the first look, it looks like it will have more overhead because here it basically means that you had one thread which was executing this. Now, if you want both of them to be executed simultaneously, you have one thread going here. So which means one more thread. So which means you need duplicate your pipeline.
Right.
So if you have, let's say, only one pipeline, you cannot have 2 threads. So you have to have a hardware support for it.
Right.
Right. And not only that, if you keep executing, so let's say it turns out that this was taken, so then you need to flush all of this. Yeah, so in terms of hardware, it will cost you more.
Yeah.
I think they have class at 4:30 here. Yeah.
Yeah, it just